Good afternoon. My name is Mariusz Dąbrowski, and I am the president of the Jerzy Stelmach Eureka Foundation, which deals with interactive science and education of the frontal scientific research. We are generally scientists who are popularizing science, and for a couple of days we offer you lectures and debates under the project Science and Technology Progress Closer to the Society, session number N2, which is Nauka in Polish, science number 2, entitled Dark Universe, Problems of Contemporary Cosmology. The project is co-financed by the Polish Ministry of Science and Higher Education, and its aim is to bring the achievements of outstanding scientists to the general public. Today, I am pleased to announce that the lecture, the following lecture will be given by our special guest, Professor Leandros Perivolaropoulos from the University of Ioannina, Greece, who will give a talk entitled Underlying Cosmological Tests and the Current Cosmological Tensions. Hello, Professor Perivolaropoulos. Hello, Leandros.
Hello, nice to see you. It's a pleasure to be here. Thank you for the invitation.
Thank you very much. Let me say a few words about the today's speaker and about his outstanding career in science. Professor Leandros Perivolaropoulos is a professor in the Division of Theoretical Physics at the University of Ioannina, where he has been a faculty member since 2002 and has held the rank of professor since 2010. He was studying for the BSc at Ioannina in the period 1981-1985, and then changed to Brown University in USA, where he first presented his MSc project, and then defended his PhD in 1991. He was also a postdoc at the Harvard-Smithsonian Center for Astrophysics, and also a research fellow at Massachusetts Institute of Technology. He is really a prolific researcher in theoretical physics and cosmology, with over 160 citable papers and more than 11,000 citations. The so-called Hirsch index is around 50. Various sources tell different values, but it's around 50, which is quite an achievement. And what is very characteristic, and I can personally admire this, that he single-authored around 40 of his 160 papers, which is not very common nowadays, but it tells about strong individuality of our guest today. His recent work has been at the very forefront of investigating the topics which he will discuss with us today, which means he's an expert in the problem of Hubble tension, modified gravity models which means dark energy models, in fact, because why we modify to actually entertain the dark energy into our scheme. And also evolving challenges to the lambda CDM model. The lambda CDM model is the standard model which admits the cosmological constant as the dark energy, as I have been talking during my lecture an hour ago. Okay, I think we really will enjoy the lecture by Professor Perivolaropoulos. I would like to once more just say that we are sponsored by the Polish Ministry of Science and Higher Education. And now let me give the floor to Professor Leandros Perivolaropoulos. And please, Leandros, start your lecture. So please share the screen and start your lecture about the cosmological tests and problems. Okay, I can see full screen, perfect. Welcome to the lecture.
Okay, thank you very much, Mariusz, for this kind introduction. Can you hear me well?
Yes, perfect. Yes, okay. Everything is perfect.
Okay, thank you again for the invitation. It's a pleasure to be here and giving this talk in front of this general audience. And what I'm going to focus today is to give an overview of the current status of measurements and models in cosmology, and especially I will focus towards the second part of the talk on the tensions of the standard cosmological model, which is lambda CDM. Now, let me start by reviewing the four fundamental interactions of nature. As many of you probably know, the four main forces that determine the future of the universe and of our everyday life is the strong nuclear force, which is the force which binds the nuclei together. And second is the electromagnetic force, which determines, of course, light, chemistry, and atoms. And it's long range, but screens because it has positive and negative charges. So you can have neutral atoms, for example. Then there's the weak nuclear force, which is responsible for radioactive decay for various nuclear interactions. And this is a very short range force also. And also there is the gravitational force, which is the universal attraction between all mass and energy in the universe. And the special feature of this force is that it's, in fact, it's long range and it's not screened. So it's always attractive. It cannot be, there is no negative mass to screen the gravitational force. And so this makes it a special force in the context of the universe because it acts on very large distances. It's the dominant force that acts on very large distances. So here you see a picture of the forces, the strong, the weak, the electromagnetic, and the gravitational force, which dominates on large scales. So I was saying that the force of the cosmos on large scales, which dominates on large scales, is gravity. And this is because gravity is long-range force, and also it's always attractive. So you see here a picture of a galaxy which where the gravitational force dominates. And you also see that on clouds, for example, in the universe, there are maybe ionized plasma, but because there is both positive and negative charge, this part of this electromagnetism gets screened. And so the long-range force which dominates the universal evolution is gravity. Now, the central point, therefore, to understand is that the evolution of the universe, which is cosmology, it's gravity which dominates, and so we need a very robust and accurate theory of gravity. The theory of gravity, then, it's general relativity, and our modern understanding. Let me just here. Understanding of gravity is the general relativity, which is the theory of Einstein, as we probably all know. Now, the core idea here is that matter and energy tells space-time how to curve. As you see here in this figure, we have a body which curves the space-time, and curved space-time then tells matter and energy how to move. So its matter moves in this curved background. And the equation of Einstein, which tries to predict the motion of matter and energy, is an equation which on the left-hand side has geometry, and on the right-hand side has matter and energy, which is the cause of this curvature of space-time. Now, mathematically, this can be seen through this equation, which on the left-hand side has geometry. This G is a matrix, a 4x4 matrix, which is the Einstein tensor. This G small g is the metric, which encapsulates the metrics of the space and time. Lambda is the so-called cosmological constant, which measures the springiness of space. It induces a repulsive gravitational force. And on the right-hand side is this T mu, it's a 4x4 matrix, this gravitational constant G, which essentially encapsulates the so-called stress energy tensor, which basically contains the information on how matter and energy and pressure are distributed. So this is the core equation of general relativity, and in the weak field limit, it reduces to the well-known Newtonian force that we all know. And for example, if we take this in weak, for a point mass, in a weak field, in the weak gravitational field, the corresponding force becomes the usual force we have for gravitational attraction, which is this Newtonian attraction that you see here. But because of the cosmological constant, we see here you have another term, which is lambda c squared, c is the speed of light over 3 times r, where r is the distance between the two masses. And this is a repulsive term. So the cosmological constant, if it exists in nature, which we know that exists, converts the attractive force of gravity to a repulsive force which dominates at large distances. Because you see here, this goes like 1 over r squared, the usual Newtonian force for the distance between the two masses, the m capital and m small. But this term here induces a repulsive term, which shows that on large distances, gravity becomes a repulsive force. That's the new information induced by the cosmological constant. So the other thing we need to describe the universe is not only the law of gravity, but we also need to know the symmetries of the metric, the symmetries of the space-time itself. And so the big assumption we make for cosmology to make it a simple system to be able to describe its evolution through the Einstein's equation is to assume that the universe is homogeneous, that is the same at every location, and isotropic, it's the same in every direction. This simplifies very much the metric of the universe and allows us to solve the Einstein equations and obtain the evolution of the space and time of the universe itself. So here you see on the left that an example of an isotropic system. This looks the same at all locations. You see these bricks that they have here. And this here is a demonstration of what we mean by isotropic universe, which you see it's the same in all directions. Now the universe, which this is an average out view of the universe on very large scales, you see it's a system which is both isotropic and homogeneous. And this is a good approximation for the universe on very large scales, which allows us to describe it in an efficient way. So there is evidence for this isotropy. It's not just an assumption. For example, the homogeneity. For example, for the homogeneity evidence, galaxy surveys show a uniform web-like structure on scales larger than 100 megaparsec. 1 megaparsec is 1 million parsec, and each parsec is about 3 light years. So it's about 300 million light years. 300, the time it takes light to travel the space that the distance light travels if it travels for 100 million, 300 million years is this 100 megaparsec. And also the evidence for isotropy is what we call a cosmic microwave background. And this is the radiation that comes to us as a picture of the universe from its first few thousand years after its Big Bang. And this is also radiation which is extremely isotropic And it's an evidence that, in fact, the universe on very large scales and at early times, it was very isotropic. Now, the metric that describes this symmetry, this isotropy and homogeneity, is known as Robertson-Walker metric, and gives us the characteristics of the universe at on very large scales. And it has one parameter which is called K. It allows for three possible shapes of space-time. For K equal to 0, we have a flat universe, like a generalized plane. For K equal to +1, which corresponds to positive K, we have a positive or closed universe corresponding to a three-dimensional sphere, a generalized concept of the surface of the sphere in 3 dimensions. And for negative K, we have what's called open or negative curvature universe. The curvature, of course, is the same at all points of the universe, assumed to be. So it's because it's a homogeneous system. So K tells us the curvature of the universe, but in addition, the universe also expands. So it changes space. It's like a balloon which expands. So we have to introduce a function, which we call scale factor, to describe how the universe expands. And it's a measure of the size of the universe. Now, for A of t equal to 1, which is the value by convention we assume today, and for A of t less than 1, we are in the past where the universe had a smaller scale at all points. And for A of t larger than 1, it corresponds to the future when the universe will become even larger than it is today. And here you see the analogy of a balloon. Imagine that we're ants, that's very small creatures which live on the surface of a balloon. Then the distance between 2 points of this balloon increases as the balloon expands, and it's like space-time in 3 dimensions. So this is a 2-dimensional analogy, but we have to think it as a 3-dimensional space, not generalize the concept of a balloon as a 3-dimensional space. And you see as the balloon becomes larger, as it expands, and all points get further away, and in fact also light increases its wavelength. You see here the wavelength of light also increases the wavelength as it expands. Now this expression here is what we obtain for the distance between 2 points in space-time as the universe expands. You see here there's the scale factor square, which as the Chinese tells us how much the universe expands, and then this dr is the coordinate distance between 2 points. K, the type of curvature, comes here in the denominator. And we have also the time, because it's space-time, and also there's also other dimensions for the angles for the other 2 dimensions in space. And r is the distance between 2 points. And as A of t increases, the grid of space expands. And the physical distance, this ds square, or this d, is equal to the scale factor A of t times r, where r is some initial distance between 2 points. But as the universe expands, this distance increases due to the expansion of the universe, not because the actual points move, but because the space itself expands and increases. So the comoving coordinate r remains the same, but the distance between points increases because the space itself gets expanded, like in this balloon. And here you see the 3 possible curvature types for a spherical, k equal to +1, for a flat, and for negative curvature case here. So the dynamics of expansion is determined by the so-called Friedmann equations. What one needs to do that, one needs to determine the dynamics of this scale factor A of t. So one plugs in the metric of the Robertson-Walker metric of the homogeneous universe. You plug it in the Einstein equations, which are of these forms, and this yields the so-called Friedmann equations, which are the equations which determine the evolution of this scale factor A of t, and that is the evolution of the background of the universe, essentially. So this way we get the so-called Friedmann equations. This is the first Friedmann equation you see here. On the right-hand or the left-hand side here, you have the geometry, and this A dot on top is the rate of change of A divided by A, the scale factor, squared. This is 8 pi times g, where g is Newton constant, times rho. Rho is the density of matter, the smooth homogeneous density of matter in the universe. K is the curvature, which has the values +1, 0, or -1. We believe that K has the value of 0. The universe we live in is almost flat, 1/a² here. And so this equation is an equation between geometry, the rate of change of A, and matter, the density of matter, which, if we know the density of matter, we can solve and find the evolution, the predicted evolution of the scale factor, and then compare with the observations to see if, in fact, this evolution is what we observe. Now, there is a second equation, the so-called acceleration equation, the second Friedman equation. This relates the expansion acceleration on the left-hand side here to both density of matter and also pressure of matter or of energy in the universe, and also includes the cosmological constant here. This form doesn't have the cosmological constant, but here I also included the cosmological constant, which was present, you remember, in the Einstein's equation. And this A with double dot on top corresponds to the acceleration of the evolution of the scale factor. How much does it accelerate its change? So, and rho plus 3p is the active gravitational mass, because you see what causes the acceleration or deceleration of the universe is determined by rho plus 3p over c squared, where c is the speed of light. Now you see that if we have negative, you see there's a minus sign here, which shows that for positive density and pressure, we have a deceleration of the scale factor, which means the gravity tends to break, to decelerate the evolution of the universe. But the cosmological constant you see here has a plus sign, and you see it tends to accelerate the expansion of the universe, and there's no minus here. So a positive cosmological constant tends to accelerate the expansion of the universe. Now, the way that we can measure this scale factor is to use the Hubble parameter, and this can be this Hubble parameter, which is defined here, is the rate of change of the scale factor over the scale factor. This dA dt is the rate of change of the scale factor. This Hubble parameter has the important feature that it can be measured. It's observable. So through the Hubble parameter, we can measure the scale factor A of t, and therefore we can measure the evolution of the universe. Now, this parameter h is a function of the scale factor A, or of time. And so the Hubble parameter is a function of time, and so is the scale factor. And of course, it's a factor of the scale factor also. And its value at the present time, h0, is called the Hubble constant. It's the value of the Hubble parameter today, which corresponds to the time t equal to 0, the present time, or A scale factor equal to 1, which again is the present time of the scale factor. And you see, for example, that two galaxies initially would be at a distance r1 at some present, at initial time, and then at a later time they became far further away due to the expansion to another distance A of t1 times r naught. So r of t, the distance between two galaxies, is equal to the scale factor times their initial distance r0. And if we want to find the rate of change of r of t, which is the velocity of recession between the two galaxies, this velocity of recession is equal to the rate of change of the scale factor A dot of t times r naught, because we find the rate of change of both sides of this equation. Then we can multiply and divide by A of t, and we then form the Hubble parameter here, you see on the left-hand side, on this side. And so the velocity by which the two galaxies recede from each other is equal to the Hubble parameter at time t times their distance at the time t. And so if we measure the velocity between of the recession between our galaxy and another galaxy, and if we know also the distance between these two, we can in principle measure the Hubble parameter. This is one way to measure this, but we need to find the velocity and the distance. So essentially, this is the Hubble law through which we can measure the Hubble parameter at the present time. You see it connects the velocity, which can be connected with this so-called redshift. I will show it in the next slide, which is the rate of change, the change of the wavelength of radiation between the receiver and the emitter. And this is connected to the distance and the redshift. So this redshift, if we know the redshift and the distance, we can measure the Hubble parameter. Essentially, we can measure the rate of change of the scale factor today. And Hubble was the first actually who pointed this out, this linear connection between velocity and distance, and constructed this diagram, which shows that put the distance and velocity for various galaxies, velocity of recession, and show that they lie on a line, and this line, this connection between V and D, is known as the Hubble law. This is a very early, of course, plot. This is one of the first plots that was created by Hubble in 1929. Now, the question is, how do we actually measure this Hubble parameter and therefore the scale factor A as a function of time? And for this we want to map the expansion history, h of A. And the question is, how do we do that? We need two pieces of information for any given object like a galaxy. The first thing we need is the recession speed, which we can obtain through the so-called the redshift. Now let's see what's the redshift. Due to the expansion of space, light of distant objects gets stretched to longer render wavelength. Longer wavelength means render wavelength. So we can see how do some lines of various elements shift as we observe galaxies which are further away. So we can measure the cosmological redshift Z. And this redshift directly tells us the scale factor A of t. Through this relation, the redshift is defined as 1 plus z is equal to the wavelength we observe we observe today here at our laboratory, which is the observed from a galaxy, and over the wavelength that was emitted from the galaxy, which we can find by looking at various elements, see what's the line, the sets of lines which were emitting the emitting spectrum. So we divide the observed wavelength from the wavelength that was emitted. This is equals to 1 over the scale factor, because the scale factor is the one that makes the wavelength bigger due to the expansion. So the observed wavelength should be corresponding to the present value of A of t, which is 1. By definition, we assume that A of t0 is 1, and the emitted should be proportional to the to the scale factor at the time of emission, A of t. So in this way, if we measure the redshift, this ratio, we measure essentially the scale factor at the time of emission when it was emitted from a galaxy. Now, the second thing we need here is the distance, and it's hard to actually obtain the distance. We need the so-called luminosity distance, dl, and dl is what we measure, and it depends on the integral. Integral is an integral of the scale of the Hubble parameter as a function of the scale factor or the redshift. So we have this relation between the distance of the galaxy which is observed at the immeasurable redshift z, or at the scale factor A, because of this relation, which is equal to 1 plus the redshift times this integral from 0 to the scale to the redshift z of c1 of something over the Hubble parameters h of z prime. Now, for small z, this integral becomes the connection between the distance and the redshift, which is essentially the Hubble law at the present time. So this law here is the general case for the Hubble law, which I showed in the previous transparency. It's much more general because this is valid not only for the present time, but for all redshift z. But for small z, it becomes just the well-known Hubble law, which connects the redshift with this Hubble parameter and the distance. So once we measure the distance at various redshifts z, we can construct this dl of z, and from this we can find this Hubble parameter at various redshifts or at various scale factors. So we can measure, in principle, if you can measure distances, this h of A, which is the Hubble parameter as a function of the scale factor, and the key thing is to measure distances for various redshifts. Now, how do we measure distances? That's the key find, because to find the Hubble parameter, we need to measure distances at various redshifts, at various scale factors A, or at various redshifts, which is equivalent. So we use two main ways to do that, to measure distances at various redshifts. One is to use some objects which are known as standard candles, and these are objects which have known intrinsic brightness, that is the power of radiation they emit is known, and this power, energy per unit time, is called luminosity, capital L, or absolute luminosity. So what we do, we assume that we have this object which has known luminosity, then we measure its apparent brightness, the flux, which is energy per unit length, per unit time, per unit surface. This is the flux, and we calculate the distance using this formula here, F equal L, the luminosity distance, over 4 pi dl squares. Here you see a figure. You see, for example, a standard candle like a supernova, which emits radiation, emits energy per unit time, and this is distributed over this spherical surface, which has surface equal to 4 pi dl, where dl is the radius of the sphere. This is the surface of a sphere. And so the flux, the energy per unit time per unit surface, is equal to the total energy per unit time, this L, divided by the total surface of the sphere, which involves in their distance, the luminosity distance dl. So if we measure the flux, the energy per unit time per unit surface on Earth, and if we know L, the energy per unit time emitted by the standard candle, or luminosity, absolute luminosity, then we can measure, we can infer this distance to the supernova. The analogy is what we know. If you know that we have a light bulb of 100 watt, for example, you can judge distance by how dim it appears if it's in a distance. A dimmer bulb, a dimmer light bulb will correspond to a larger distance, given, assuming that it has a fixed and well-known power of emission or energy per unit time. So these are the standard candles. And the second way we can measure distance using the so-called standard rulers. And these are objects with known intrinsic size or length, which I call it here S. So we measure the apparent size, the angular size delta theta. You see, we have this ruler here. We measure this angle theta, which is the angle by which we see the ruler. We calculate the distance then from the formula where theta is equal to the scale of the ruler, the size of the ruler, RS or S that I saw here, divided by the distance. So this is this dl, dA is called the angular diameter distance, and this has a similar expression as dl, not exactly the same, but similar in terms of h of z, the Hubble parameter in terms of the redshift. Now the analogy here is that knowing that a car is, for example, 5 meters long, you can judge its distance by how small it looks the further away it is. So if it looks very small and you know its size, it means that it's a large distance. If it's bigger, it means that it's smaller distance. So it's a connection between how big the angle is, which we see in the car, and the distance between you and the car. So this is the second way, therefore, to measure distances using standard rulers. Now, the challenge in cosmology is to actually find the reliable standard candles and standard rulers in the distance universe, because we cannot use a car, of course, or a bulb. We need a very powerful sources and very clear, well-known rulers in a very distant universe. And the more distant it is, the further away we can find the Hubble parameter as a function of z. Now, the best standard ruler we have is the so-called sound horizon. And to understand this ruler, we must think a little bit of how the so-called cosmic microwave background was produced, how it comes to us. Now, in the early universe, very early universe, when the universe was about more than 1,000 times smaller than today, corresponding to redshifts larger than 1100, then the universe, there were no atoms because the photons and was very, very energetic and would dissolve all atoms. And so the universe was a hot, dense plasma of photons, electrons, and protons, that is, protons and neutrons, or baryons. And this was a soup. You see here, there was photons constantly scattering on charged particles like electrons and protons. And photons tend to scatter on charged particles. As the temperature of the universe started to cool, the plasma was initially opaque and photons were trapped in this plasma. And in this primordial soup, pressure and gravity were competing, and there were oscillating regions. Initially, we had a region which was was trying to collapse by gravity, but then there was a pressure from the photons, and then it would expand again, collapse, expand, because pressure from the photons and gravity were competing forces. And so we had this so-called sound wave oscillation. We had sound waves which were expanding because of these effects of the pressure by the photons. But all these things stopped suddenly at about 1100, reached 1100, because the universe was 1100 times smaller than today. At the time of recombination, the temperature started dropping because of the expansion. Larger expansion means smaller temperature. And so the photons did not have enough energy anymore to prevent atoms from forming. And so at some point, electrons and protons combined to form neutral hydrogen, and the first atoms formed. When the atoms formed, they were neutral, and then photons could not scatter on them anymore, because photons do not interact directly with neutral atoms. So the photons became free, the universe became transparent, and the photons streamed freely, forming the cosmic microwave background. Now, these photons, which were then released at that time, are reaching us today from all directions, and they are almost the same from all directions, and they constitute the cosmic microwave background, give us essentially a picture of the universe, a photograph of the universe, at a time when the universe was very young. Shortly after the Big Bang, about 380,000 years, which is very close compared to the present age of the universe, which was 13.8 billion years. 300,000 years is very early in the universe evolution. So these photons bring us the picture of the universe as it was at the time when it was very young, shortly after the Big Bang. Now, these photons have the feature, which is predicted, they have a very characteristic spectrum, that is intensity versus wavelength, which you see here, which corresponds to the so-called black body. It's the same temperature, the same form of spectrum as the sun, but here we have a much smaller temperature. It's only, today it's 2.7 degrees Kelvin, because it has reduced due to the expansion from that time. But as in the case of the sun and in the case of the plasma, we have the same mechanism for forming this spectrum. And also in this picture of the universe, we also see the primordial fluctuations. This is the CMB. These are the photons that come to us as obtained from the satellite Planck, which recently, a few years ago, obtained a full picture of these fluctuations, even though we knew them since the 1990s, when Kobe was the first satellite to observe them. Now we know them in much more detail. So you see here, they are more or less homogeneous and isotropic. But if you go down to 10 to the minus 5 Kelvin resolution, then you see that there are some primordial fluctuations in this picture of the universe. And these are the fluctuations which evolved until today, and they form structure. Gravity was acting on them, and matter tried to collapse on them and formed galaxies and cluster of galaxies. And our planet also was believed today. So if you want, these fluctuations is like our grandparents. Our existence is due to them. They were the fluctuations which produced the galaxies and the planets which we know today. So these fluctuations are seen there, and the sound horizon is the maximum distance sound have traveled from the Big Bang, the creation of the universe through a singularity, until today. We can calculate the sun horizon scale, this kind of distance that sound has moved by today. And this is our standard ruler. We see its imprint as some peaks in the cosmic microwave background. And let's actually see how it was produced. Before recombination, we have the plasma, which is coupled to photons. And this led to expanding spherical sound waves, which emanated from barium gas, by photon pressure. We see here such a wave which is expanding. Now, at recombination, these photons stopped being scattered, they free stream, and the pressure becomes negligible. And at that time, the spherical cells of baryons freeze at a given size. And this size is very important. We can observe this today in various ways. First of all, directly in the CMB, but then also on the perturbations and on the structure that form today, because these imprints actually give a signature in the structures in the distribution of galaxies we see today, because they have characteristic size. Here you see an evolution of the coupled photon with gas. Gas is the neutron electrons with protons, and you see that initially photon, the red and blue, the gas, are coupled together. So you see here, initially here the red, you see here this line, they are coupled together. At some point the photons, the red decouples, goes away, but the baryons remain here. And they have this, and then the black, which is dark matter, comes and collapses on top of the baryons, and we have structure formation. And the structure is what we measure today, and we measure the standard ruler essentially through the CMB directly and also through the structure today. And here in this figure, you see this spherical wave, which initially expands for a while, here on the left. You see here this spherical structure, which expands initially, then stops at the time of recombination, and this spherical wave of sound wave stops there and it stops over here from various sites in the universe, and this becomes seeds for matter to accrete on them and form the so-called baryon acoustic oscillations, which are this characteristic scale. That's where galaxies tend to accrete on top of these initial baryonic shells. And this galaxy is what we measure today, and we can see the distribution, the distances between these galaxies, and we see that in their distribution is imprinted this characteristic scale, which we can measure today, and in this way we can measure distances at various redshifts. So you see here, these are the galaxies, and you see that if you find the number of galaxies per distance, you see that at all distances there are galaxies, of course, but there are more galaxies distributed at this particular distance, at the distance of the sound horizon. And you see there is a peak in the number of galaxies per distance at this characteristic scale, which is about 150 megaparsec. You see here there's a small peak here of galaxies, and we can see can measure the angular size of corresponding to this scale at various redshifts, and then we can actually use this to measure distances at this particular redshift. So we slice the various redshifts, and then we measure the angular scale of the baryon acoustic oscillations, and from that we measure the distance at this redshift versus redshift. So this is the way we use this standard ruler, and the next question is, what are our best standard candles? Because we saw what is the best standard ruler, we want to find also the best standard candle, and this is the so-called type 1 supernovae. And these are explosions of a white dwarf star, a small star which has not enough mass to become a sun, to become a star. It's a white dwarf which doesn't shine yet, but reaches a critical mass, which is called the Chandrasekhar mass, which is about 1.4 solar masses. And when this mass is reached by the mass it accretes from a companion star, then an explosion happens, a very powerful explosion, which is as powerful as a galaxy, as a full galaxy, but lasts for a short amount of time. And these are standard candles because they all explode at the same mass, and their intrinsic luminosity is incredibly consistent. It's almost the same for all of them. So if we know the standard luminosity, intrinsic luminosity, and we measure the apparent flux, we can find their distance dl, as we see in this plot that we showed also before. We measure f, l, and we infer dl, and we construct this curve here, the curve which is the absolute magnitude of their luminosity as a function of time. Days is in the horizontal axis. You see there is a peak at the time of the explosion, and then all these curves drop. They are very similar to each other, but we can actually make them exactly the same by calibrating them through their color and through their stretch, the size of their light curve, which we see here. So we can more or less make them almost identical, and we can have a very good measure of their absolute luminosity, which we plug in this relation here, and we find their distance. And using their distance, we can actually measure h of z. The way this is done is we use the so-called cosmic distance ladder to measure the local value of the Hubble parameter. And so we use three ranks. In the first rank, we go to some stars called Cepheids, which have very characteristic features about their luminosity, which I will talk later on. So we measure their distance using geometric methods. This is the Sun, this is the Earth. We can use this triangle here. And since we know the distance between Earth and Sun in this triangle, and we know also this angle here, we can infer the distance between the Earth and the star using the so-called parallax method. So this is the solar system here. Now, once we know the luminosity distance to these stars, we can infer their absolute luminosity, and we can correlate them with a period, because these are pulsating stars, and there is a correlation between their luminosity and their period of pulsation. So we can calibrate them consistent by making this curve here, this straight line. So once we make this this line, we can know the luminosity of a Cepheid by just measuring its period, how rapidly it pulsates, and we can infer the luminosity. Now, once we know this relation here, the connection between luminosity and period, we can go to find Cepheids in nearby galaxies that also called type 1 supernova, which are extremely bright, and calibrate the supernovas using finding the true brightness of the supernova. Since we know the distance, we can find out the brightness. And once we calibrate the brightness of the supernova and we know what is the absolute luminosity and its connection with their color, etc., then we can go to further away galaxies which are in the so-called Hubble flow, which are within the expansion of the universe, in the area where the universe clearly shows its expansion rate. And we can actually find the distance to this supernova and then obtain the Hubble parameter using the connection between the distance and the Hubble parameter. So this figure here summarizes 3 steps. The first step is the first rank is the distance, is the geometric determination of distance to Cepheids. The second part is the finding the luminosity of supernova that are co-hosted in galaxies with Cepheids, and the third is go to the Hubble flow, to the very large scales where the expansion is apparent, and then actually measure the Hubble parameter in terms of redshift. So this is the way that we measure the Hubble parameter, and the first surprise was that if we measure the Hubble parameter and the actual as a function of the redshift, we find something very interesting, which was found about 25 years ago, that distant supernovae at jet larger than 1, about when the universe was about half its size today, were dimmer than expected. And this means that they are further away than they would be if the universe expansion was slowing down. And this means that the universe is accelerating. So this is the Hubble diagram you see here, essentially distance versus redshift. And you see that the way it goes, the distance is larger in galaxies than we would expect in a non-accelerating universe, which indicates that in fact the universe is accelerating, it's increasing its expansion rate, increases h of z, increases with redshift as we go at late times. So this means that since we have an accelerating expansion, you see here this A double dot is the acceleration of the scale factor, it means that this right-hand side should be have at least one component which is negative, so that this minus sign becomes plus. So we have rho plus 3p to become to be negative, which means that pressure must be less than 1/3 times the density. Now, what is this new component which has this feature, which has negative pressure? This is what we call dark energy, and this is what causes the accelerating expansion of the universe. Now, the pressure in general for a fluid is equal to some parameter W, which is called parameter of equation of state, times rho. And this means that rho times 3W, we demand that rho times 1 plus 3W should be less than 0. So for accelerating expansion, we demand W less than minus 1/3. Now it can be shown also that the density of the universe scales like the scale factor to the minus 3 times 1 plus W, which means that if we want to have a cosmological constant, a constant density, this W must be equal to minus 1. So the best fit indeed, according to the Hubble parameter as a function of time, is that this W is equal to -1, which means corresponds to the cosmological constant lambda, or equivalent to a constant energy density of dark energy. So dark energy is not only has negative pressure, but also has another feature based on observation, which seems to be close to being -1, corresponding to the cosmological constant. So we know now, based on measurements, that most probably the dark energy is actually a cosmological constant. Now, so this brings us to the standard model, the so-called lambda CDM, where this lambda stands for cosmological constant, which corresponds to an equation of theta equal to -1. And also there is cold dark matter, that is an unknown non-interacting particle that provides the gravitational background, the gravitational gravity for within galaxies to form. So the universe today, as we know, that is our lambda CDM model, the best model we have, consists of about 70% of its energy corresponds to the cosmological constant, this omega lambda, which is usually called. 25% of its energy is the dark matter, and about 5% is normal matter, baryons, which is the matter we are made of, and galaxies are made, the sun is made of, planets, etc. And this model has been successful for over 20 years. This, you see here the pi of the distribution of the energy, of the dark energy. Now, the first tension here that exists is the so-called H0 tension. And the measurement of the Hubble parameter using two methods, the early universe and the late universe, provides, for example, using the CMB, the Planck measures, using the standard ruler, the sound horizon at z equal to 1100. In first H node using the lambda CDM model, but also we can measure this directly using supernovae and this distance ladder method I mentioned before using Cepheids and supernova. Now the problem is that these two methods, here you see the standard ruler which can be used. We measure the theta to the standard ruler to the sound horizon. We calculate sound horizon using some integral, using the early universe before recombination. And so we infer the distance to the CMB, the scattering surface, using this method. And the measurement of these in these two ways provide two different numbers. One is low, as when we use the standard ruler, which is used at the very early times, at the early universe, and the other is much higher, which is the one obtained from the direct measurements of H naught using supernova. So the question is, why do we have this disagreement? And we have to look at the assumptions made in this case. In the case of the sound horizon, we assume that the RS, the sound horizon, is calculated correctly, and also that the expansion of the universe from today until the CMB, until the time of recombination, is the one predicted by lambda CDM, which is given by this kind of form here. So this is a big assumption. Some of this could be incorrect. And so resolving the Hubble tension includes two possibilities. One is there are some unknown systematics, and the other is that the lambda CDM model is wrong and needs to be changed, and especially with respect to the early universe case. So one way one could do is to change the scale of RS, the sound horizon, at early times. And this can be done by introducing some early dark energy at early times, which would change the expansion of the universe as we know it. Or introduce some dynamical dark energy at late times, which would take us beyond the cosmological constant. So here you see h of z over 1 plus z as obtained from the data from the standard lambda CDM model. And you see it goes to h0 here, the 0 goes to about 67, corresponding to the measurement from early universe. And this is the measurement from the late universe, the direct measurement. You see that there's a disagreement between the two. And the way to resolve this would be either to assume that there is some problem in the intrinsic luminosity of the supernova, there are some systematics, for example, and in that case we would move this blue point down to make it consistent with the early universe measurement, or we can change the sound horizon scale in this connection between the angle of the sound horizon and H naught. If we decrease, if you decrease, for example, RS, you increase H naught here. And so it's like moving this whole line up to make it consistent with the single local measurement we have here. Or we can deform, for example, this line by introducing late dark energy, dynamic dark energy, which would deform it and make it consistent with this recent measurement. So change essentially the expansion, this H of Z, to make it consistent with the present time. Now, so this is the Hubble tension, and these are the models that actually can be used to describe it. And this brings me to the second area of tensions, which has to do with the growth of structure. Now, the expansion history H of Z, of course, is not the whole story. We have the background, but there's also the growth of fluctuations, of primordial fluctuations, which we saw from the CMB, which also are the ones which lead to the existence of structure in the universe. And in the early universe, of course, matter was very smooth, but there were some fluctuations, as I showed in a previous slide. But over the age of the universe, gravity pulled matter together to form the cosmic web of galaxies and clusters we see today. And this growth is a battle between gravity and dark energy, which has this repulsive force I showed before. So the combination of the two leads us to the observed structure that we see today, galaxies and clusters of galaxies, which can be predicted on the basis of lambda CDM model. If we fit lambda CDM to the CMB, to the primordial fluctuations we measure in the CMB, and we evolve through simulations, through computer simulations, we can make a prediction, a precise prediction of how fast structures should grow, and we can measure therefore the growth rate in the local universe to see if it matches the predictions of lambda CDM. And the problem is that, in fact, since we have the seeds from the CMB, we know the initial perturbations, and we can use lambda CDM, and we can predict the large-scale structure, that is how clumpy is the universe today at z equal to 0. And we can parameterize this clumpiness using this parameter so-called sigma 8, which is the initial amplitude of matter fluctuations at 8 megaparsec scales. So from the CMB, we go to the structure through lambda CDM, and we compare with fluctuations. And this comparison can be made usually through a single parameter, which is called S8. And this is equal to sigma 8, as I said before, the amplitude of matter fluctuations at 8 megaparsec scale, multiplied by the square root of omega matter, the density of matter, which is the driving force of gravity, if you want, for the clumpiness of for the growth of structure. So we have the gravity, the driving force of gravity, which is the density of dark matter, and we have the amplitude, which is S8, the sigma 8. The combination of the two gives us this S8 parameter, which is a measure, an observable measurement of the growth of structure. And we can compare the S8, which is predicted by the CMB under the assumption of lambda CDM, with the directly measured S8 from the local large-scale structure surveys. And we can measure this in 3 ways using weak gravitational lensing. So we see the distortion of galaxies as light from other background sources, like, for example, quasars. How much are they distorted because of matter, of structure. And this directly maps the invisible dark matter clumps. We can see how the galaxies are distorted by dark matter. So we measure the dark matter clumpiness this way. Second way is to measure the so-called redshift space distortion. We have a round, for example, a spherical region with an overdensity. Because it collapses, we have the redshift on one side goes one direction, the opposite side goes the other direction. So in redshift space, using the Hubble law to measure distances, it looks to us like this is squeezed. And this degree of squeezing can be used to measure the peculiar velocities, that is velocities due to clumpiness, due to growth of structure, and compare them with the one expected in the context of various models. So we have, this way we can measure the peculiar velocities as they fall into overdense regions. And this redshift space distortion can measure this infall, would tell us about the growth rate. And the third is to use cluster counts, which is galaxy clusters are the largest objects, and counting them as a function of mass and redshift is sensitive to measuring this parameter S8, the growth of structure. Now the result is that S8, which we predict from the CMB using the standard model, is bigger, it's 0.83 plus or minus 0.01, compared to the one which is measured, which is smaller, it's 0.76 plus or minus 0.02. And it shows that the growth, this is called growth tension. It indicates that the universe seems to be less clumpy than expected in the context of lambda CDM model. And the question is why? Could it be because gravity is not really what we expect it to be? It's not general relativity, and so we have weaker gravity, which leads to the growth of structure. Could it be that we have less dark matter than we thought in the context of lambda CDM? Whatever is the reason, it's one of the puzzles of one of the tensions of the standard cosmological model, and there are currently various papers which attempt to explain this. In addition to these measurements, we also have the recent DESI results, which are, it is an instrument in Arizona, which measures these baryon acoustic oscillations at various redshifts, and this way it constructs the evolution of dark energy and compare this to lambda CDM. And it looks like, in fact, here there is some hint for dynamical dark energy, which means that this W of Z does not seem to be equal to -1 as in the case of lambda CDM, but there is a tendency to be less than -1 at high redshift at early times, and larger than -1 at very late times, which means that there is an evolution of the organizational state, an evolution of the density of dark energy. And this is one issue that actually during the last 6 months or 8 months or so has been puzzling the scientific community. Why does this instrument seems to favor dynamical dark energy compared to lambda CDM? And this is a 2 to 3 sigma effect, which has been puzzling the community. It may indicate, in fact, that dynamical dark energy is a problem. Now, the third tension, which I'm going to close with, is this so-called the cosmic dipoles. Now, the H node and S8 tension challenges, of course, lambda CDM, but there is a more fundamental challenge for lambda CDM, which is the so-called the challenging the cosmological principle, that is the homogeneity and isotropy of the universe on large scales. Now, the CMB dipole, that is the distribution of the cosmic microwave background, points to the direction of our velocity with respect to this frame, where the CMB is very much close to being homogeneous and isotropic. Now, if we go to look at very distant objects like quasars or radio galaxies, we should see them to be homogeneous and isotropic around us if we subtract, of course, our velocity from with respect to the CMB. If we go to the frame where the universe should be isotropic and homogeneous. However, what is found is that even quasars at very large distances, and after having corrected for our velocity with respect to the cosmic microwave background frame of isotropy, even so these clusters should be homogeneous and isotropic, they are not. And so this challenges the cosmological principle, and the question is why there is a dipole in the distribution of quasars at a very, very far away objects at the redshift larger than 2, for example. Why is this dipole there? Why is this dipole larger than expected? And why this direction is not exactly the same as the cosmic microwave background velocity that we have with respect to the frame of the CMB? So there's a 3 to 5 sigma tension, which is, of course, of some interest. So this could lead to a possible violation of the cosmological principle that perhaps indicate that the universe may not be isotropic and homogeneous on very large scale. So in that case, the Robertson-Walker metric would not be the best metric to use to describe our universe, but would only be an approximation. So it's possible that either it's a statistical fluke for this quasar dipole, or the universe is not truly isotropic on largest scales. And if it's not, what is the mechanism that creates this fundamental anisotropy of the universe on such a very large scale, which would violate the cosmological principle? So if this cosmological principle is wrong, the FRW metric is also incorrect, and this implies that lambda CDM and the Friedmann equations are just an approximation. So we would need a more fundamental theory to describe the universe on very large scales if these dipoles indeed are there. So in conclusion, The question is, are we in a crisis in cosmology? It's clear that the lambda CDM model has very big successes in various aspects, and using only 6 parameters, it can predict various aspects like the CMB and the large-scale structure with just 6 parameters. However, there are some tensions. 3 of the most important is the Hubble tension, the S8 tension, and the dipole tension, which tend to indicate that perhaps the universe expands faster than predicted by the CMB and the lambda CDM, and also that the universe is smoother than predicted by CMB and lambda CDM, and also that matter distribution may not be isotropic, and this could challenge the cosmological principle. So these challenges are very interesting for cosmologists because they create the motivation for looking for new models to go deeper into physics. And we're in a new era of precision cosmology, and our standard model is feeling the strain. So new data from various measurements will find systematics or confirm new physics like dynamic dark energy or new components or an isotropic cosmos. Thank you for your attention.
Thank you very much, Leandros, for this very exciting talk and very comprehensive, dealing with all the tensions in cosmology, including this dipole tension, which is not often, sometimes it's not mentioned, but I know that it's kind of a special topic you deal with, and I am also very happy to hear about this dipole tension in the context of anisotropy. I am now looking at the questions which perhaps somebody was asking on a chat here and on YouTube. Are there any questions on YouTube eventually? Do we have any? If not, I may ask one single question, because you mentioned in one of the slides the possibility of having the phantom dark energy. And what is your opinion about the current? Because I was mentioning it in my talk an hour ago. And what is your opinion about current status of this phantom dark energy?
I think that the phantom dark energy is starting to be resurrected, because those of us who are for some years in this field remember that it had reappeared about maybe 20 years ago when the first time of dark energy had appeared. Now, this phantom dark energy you see here has to do with this equation of state of dark energy being less than -1, which means that the universe accelerates very rapidly, much more rapidly than the cosmological constant at early times. But now, according to this DESI data, at very late times, there is a lower acceleration than the cosmological constant would predict. So this kind of feature, this phantom, is it seems to have reappeared in data. I'm beginning to think that maybe it's even real, but of course I have some doubts. But if it's real, it has very profound implications for theories, because it's very difficult to reproduce this kind of behavior, this crossing of the phantom divide line, this crossing of the -1 line, using theoretical models. Most of the models that we know today are unable, especially quiescence, as we know, this simple scalar field with general relativity, is unable to produce this type of behavior. So for us, cosmology is very interesting because it limits very much the theoretical model. In fact, I would dare to say that it may be even hint of modified gravity, because it can only be reproduced, or maybe I should say the simplest and more generic way to reproduce this phantom dark energy, which also crosses this phantom divide line, this -1 line, is using modified gravity models at late time. So this is called extended quiescence, or scalar tensor quiescence, for example, could reproduce this. So this gives us an interesting, if you want, avenue to constrain, if it's true, of course, if it's verified also in the future by data, it gives us the opportunity to rule out a lot of models and focus on some very interesting models, which is also generic, because modified gravity, change of general relativity is a generic kind of class of theories. So I think it's exciting times in front of us with respect to this finding.
Okay, thank you very much. I don't see more questions. And in order to summarize, I would like to mention that we are working on the session N2, Dark Universe Problems of Contemporary Cosmology. We have already had 4 lectures, as you see on the slide here. That's the one is underlying cosmological tests and the current cosmological tensions. And I would like our audience to join us for tomorrow's discussion, which will be 5 p.m. Central European Time, in which we will try to speculate really on the problem, when will dark matter and dark energy be discovered in its in its real nature, not a kind of a phenomenologically or effectively in the field equations, but in its real nature. And I would also mention that our project is run under the co-financing by the Polish Ministry of Science and Higher Education. And thank you very much, Leandros, for your wonderful talk. And thank you very much for the people who attended this talk both on Zoom and on YouTube. You were the hosts of the Jerzy Stelmach Eureka Foundation here from Poland, Szczecin. And I would like to wish you all a very nice afternoon and the evening. Thank you very much and goodbye.
Thank you very much also. It was a pleasure to be here. And see you tomorrow then in the discussion. Okay?
Thank you very much. Thank you.
Bye-bye.